Hello.
Hello, Mr. Aaron, Mr. Ryan. Happy Kids Day, okay? Happy Children's Day today.
Really? I thought it said November 20th.
I don't know, okay. So last time, right, 2 weeks ago, we talked about this combination number, remember? If you are at this point, from lower left corner, 0, 0, and then at one step, you can go right or go up, right? You cannot go left and you cannot go bottom. And we're going to reach this point, which is n. And then the number of ways, remember? How do we do this? It's C to n, right?
Pascal triangle.
Yeah, it's related to Pascal triangle. So basically, right? So you can go one step to the right. So how many steps to the right? If you need 2n step, right? 2n step. This is n. This is n. You need total 2n step. It's equivalent to saying, okay, for this 2n step, you want to pick n step to go to the right. It's the same thing as you pick n step to go to the north. So the total number of ways, C to n combination. Right, this is related to the Pascal triangle, remember? 1, 1, 1, 2, 1, right? 1, 3, 3, 1, okay? And then what's next? 1, 4, 6, 4, 1, okay? So, any question about this, right? Still remember, we can use the dynamic programming, right? So for each one, FAB is equals to, coming back to the left, A minus 1B plus FAB minus 1. This is the recursion formula. Right? For adding any point, you can only reach this point from this point, from the left or from the bottom, right? And then we don't actually care how to get this point, reach this point or this point, as long as we know how many ways to get to here, how many ways to get to here, and then we can solve this out using the dynamic equation and putting the cache. Okay? And then we also talk about one interesting problem, like, if we are not allowed to cross the diagonal, okay, this is the key point today, right? We only can stay in the upper area. This area, there are dinosaurs there. We don't want to go there, okay?
What?
Yeah? So how many ways, right? We can stay using the dynamic programming, right? As long as we fill this, the bottom right corner, every f function, f values here will be set to 0 because there's no way to get to here, okay? Yeah? And to calculate this, right, we can use the top down or bottom left, right? We can start from here, right? We can start from here and then say, okay, how do we get this number? We need to calculate the number here, and then we can calculate the number here, right? And then recursively, how to get to here? We need these two values, okay? Or we can start from the left bottom corner. Here is 0, 0. How many ways to get to here? This is 0, 0. That's one way. How many ways to get here? 1, right? How many ways to get here? 1, right? How many ways to get here? 1, right? Yeah, these borders are all filled with the value 1. Okay, there are 2 ways. Okay, so how do we compute this? Without the dynamic programming in mathematics, how do we calculate the number of ways to get to this point without touching the bottom right? This is the topic today. Okay.
For what?
Pascal triangle.
No. Do you still remember? We want to calculate.
I know.
Yeah.
I missed what you just said.
Is it like Pascal triangle and then subtract the right side?
That's very good thinking. Yes, we can, because we know, right? We know the total number of ways C to n, right? Then we want to subtract the invalid path, which is crossing the danger line. Then the remaining will be the valid, right? Am I right? This is the total number of ways, right? Eric, you have questions?
Where can we not go?
The bottom left. So you cannot stay.
Bottom right.
Oh, bottom right. Yeah, bottom right. Yeah, this part. You are not allowed to come to this part. You can. So for example, 2 ways. If there are 2, okay. Let's see the easy, smallest example. From here to here. Not crossing this. You can touch but not crossing. So how many ways? 1, 2. There are only 2 ways, right? You cannot do this. You cannot do this. You cannot do this. You can only do this. Only 2 ways. You are not allowed to cross. You can stay. You can stay here. Stay in the diagonal, but you cannot cross the
Yeah, but
diagonal.
why can't you not cross?
I said that diagonal there.
Yeah, get on.
Okay,
Yeah.
I believe your
Did we already
dinosaurs
do
were-
that last time?
no, we talk about that. Yeah, we talk about Catalan, but we want to know why this time. Okay, so okay, this is
It's
much.
basically the same thing.
What's the thing?
You just add them up, like add ones on the.
Yeah, we can add this. Yes, as I said, dynamic programming. Yes, but today I want to talk about how to calculate without dynamic programming. This is for computers, right? If you have a computer, you write a Python program, easy. But I want to solve this mathematically. Okay, so how? Okay, so easy. Okay, listen, this is the key point. Okay, yeah. So let's say the coordinates on the diagonal is kk, right? K step right, k step up. So kk. The first time it crossed the danger line must be k plus 1k. Am I right? Right? It must be stepping to the right. Does it make sense? Now we can get that. The first time it crossed the danger line must be reaching the k plus 1k. Okay? So for example, k plus 1k here. So if look at this red line, right? K plus k. If we here, this is the danger point. The first time we step into the danger area. And then if we do a mapping, do a mirror on this red line. If we do the mapping on this red line, okay? So here, right? So this we do the mapping will be this one, right? Look at this point here. The usual path will be reaching this, right? If we do a mapping to this red line will be one step down the diagonal, right? Parallel to the diagonal. If we do the mapping to the mirror line, you'll be coming to this point. This is n plus 1, n minus 1. Okay, so in other words, it means that for every invalid path, the k, for any k, the first time it step to the invalid zone, I can always do a mirror to this line, k minus 1. Let's say this line is k minus 1. And then we will reach the destination n minus 1, n plus 1, n minus 1. Okay? So in other words, if I start from here, if I get to this point, if I have a path reaching this n plus 1, n minus 1, if I do a mirror, I will be reaching the mn. Okay, this is a one-to-one mapping. So what does it mean? So how many points to get to this? How many points from here to here? Is it c to n minus 1, right? Because there are n, how many steps? There are 2n steps. I want to pick n minus 1 to get to this point.
I don't see what's the point of doing that, and you can't go out of the.
I'm just doing the mapping. So from k to k to the danger zone, invalid path, right? The invalid path must be happening at some point from k to k plus 1k. Agree?
Yes.
Oh yeah.
Yeah? So after I reach this k plus 1k, I can do a mirror to this red zone and then changing the destination to this. Because if I map this, you will be reaching this point.
I know, but like, to get to that path, yeah, you need to go like right 3 times to get like out of a like map. But if you like mirror it back, so it'll end up at the actual destination NN, you'll just go out of the.
Yeah, you'll be mapping. Yeah, it will be mapping. So I'm just saying that it's one mapping. It's one mapping. So for every invalid path, you'll be reaching this point. Okay, and in other words, if I mirror this, I will be reaching this for invalid path. And how many paths to reach this point? We know, right? This is another independent problem without the invalid path, right? It's C2NN. And the answer is C2NN minus C2N. This is invalid path because we mirror it. And then the result, C2NN minus C2NN minus 1. The result is this one. If you calculate it, it will be n plus 1 C2NN. Okay? This is very important, Eric, especially for you because there are some questions. If you know it's this answer, okay, and then you'll get this. Do you understand this? Please.
Okay, but I thought you can't go in the zone. Like, you can't go to the bottom, like.
I know. That's why I'm saying this
Yeah,
invalid path.
Going.
This is invalid path. This is the total path minus invalid path. The remaining is the valid path. Make sense?
Yes. That's brilliant.
This is invalid.
It's
I'm
like-
calculating
it's like-
invalid.
it's like-
Subtract from
it's
the
like-
all.
It's like how 5 minus 3 equals 2.
Okay, but look at this one. N plus 1, 1, C2 and N. Okay, you know this, right? And this is the equation for the, this is called Catalan. Catalan. This guy, Catalan.
What's the L?
Catalan found, invented this formula. C
Catan.
N.
Catan, like the sword.
I don't know this guy.
This
1 over N plus 1 times C2 N. How is that useful? I give you one example. You know the stack, right? Stack. I have two numbers, 1, 2. I have a number, 1 to N. Going to the stack. How many ways to pop it out from the stack? You know, the valid sequence. You still remember, right? The first in, last out. Okay, let's say two numbers. How many valid ways to get the stack pop sequence? 1, 2. I show you, right? 1 first. Take it out. Now, okay, the 1, 2. Now the stack is empty. 2. Take it out. So 1, 2 is the valid sequence. Another way will be 1, 2. Now I take it out. Will be 2, 1. Okay? 2, 1. So there are only two ways, right? Okay. Can we calculate the second Catalan number from this? 2. 2 plus 1, 1. C 4, 2, right? N equals 2. So this is 3. Picking 2 out of 4 is 4 times 3 divided by 2. Okay, two numbers. 2 ways. Okay.
No, I don't get. What's that thing doing? Like, what's that calculating?
Very good. Okay, how do we get this number, right? How do we get this number? This is
No,
the...
I mean, like, what does it calculate?
It calculates the number. Okay, you can remember this. It calculates the valid way from given the n grid from left bottom corner to reach the top right corner without crossing the diagonal. How many ways?
Without.
Calculate this. Look, n equals 2, right? Remember, n equals 2. How many ways? 2, 2. How many ways? You cannot stay in the bottom half, right? We talk about that, right?
But
1, 2. Only 2 ways.
I know, but that's.
N equals
that's
2.
Yeah, but.
This is the general case.
Oh.
General case. If n is 100, you use this number. Use the equation. Why can we do this? Right. If there are n numbers, and then the sequence will be this. Why? We can compute these ways by the point that the first time the stack is empty in a way. Okay? Does it make sense? So look, if there are n numbers here, right? And then it goes out. And then at some point, the stack will be empty.
Yes.
The stack will be empty. It's the same thing as here. The first time, they cross the danger line. Okay? So why this can be similar? Because the first time crossing, right? This is kind of like, you can divide this problem into 2 stages. The first time it crosses, and the time after the crossing, it can be divided into 2 problems, right? The same thing. Another problem. This could be interesting. Polygon. A polygon. How many ways to divide this polygon into triangle without intersecting? How many ways? Let's say 4. Okay. Let's say this simple square. How many ways to divide?
No, wait.
How many ways?
2.
Yeah, you can do it this way, right? Or you can do it this way, right? That's only 2 ways, right?
Wait, that's that.
I know. Yeah, it's the same thing. Yeah. Look, if it's inside the polygon, right? How many ways you use this formula? Why? Because you can first divide this polygon into 2, and then you can solve this left and solve this right individually, and then the answer is to multiply the number of ways to divide the polygon on the left times the number of ways to divide the polygon on the right. Another problem. There are two nodes. You know the binary tree. Two nodes. How many ways to construct a unique binary tree? Let's say binary search tree. Okay, 1, 2. Right. One way. 1, 2. Right. There are only two ways, right? There are only two ways.
Why can't you go like
2, 1, yeah.
Because it's not a binary search tree, I'm saying. I mean, if you label it, it could be, you need to times 2 factorial, then there'll be 4 ways, right?
What is the binary search tree?
Okay, my bad. This is
Yeah,
the...
so how's 1, 2?
Okay, this is not a binary search tree. This is 1, 2, right? And then 1, 2, right? Okay. I mean, the structure, right? This is a binary search tree. This is a binary search tree. There are only 2 ways. If there are n nodes, right? N nodes, so you can set like 1, 2, 3, 4 to n. How many binary search tree? First, you can pick any node in the middle as a root node. Let's say I pick 3. Remember, I pick 3. And then on the left will be 1 and 2, right? On the right will be 4 to the n, right? And then how many ways? We can keep constructing the subtree of the left and the subtree of the right. And we times it together. Does it make sense? Do you see the similarity of this problem, of all these problems, like this traveling, the grid, the binary search tree, the polygon thing, and then what else?
the egg
The egg, what egg?
egg problem?
No, that's different problem. Another problem, okay, I show you.
No, just randomly.
A ticket to the football match costs like $50. £50, okay, £50.
You put the pounds before it, not after.
Okay,
No, you put the pounds before it.
I don't know how to draw that. £50, okay? £50 ticket. Then there's a ticket officer, ticket guy here. £50, okay? Ticket guy, this is the football man, this is the gate. And then there's a bunch of people queuing here. There are n people,
Yeah, and
n people with the £50 note. N people with the £100 note. Oh, we don't have a £100 note, right? Do we? Okay, let's say we have a £100 note, okay? £50
Is it like?
And
Can't you just say have 2 50?
No, because no, 100, and then this is 50, and then
Let's make
the
it
ticket.
£5 and £10.
Yeah, good point. Ticket price £5. This is the £5 note. N people with the £5 note. N people with the £10 note. This ticket guy initially doesn't have any change. Okay, he doesn't have any change.
Just pay the £5 people first.
Yeah, then how many ways to queue these people so that it doesn't have this situation that the ticket guy doesn't have £5 notes to give to the £10 notes. Same thing. Why is the same thing?
Because
At some point,
No,
the
no,
ticket
no.
guy will be having no change.
Can you just say?
Wait,
Can you just say
this
paid
is
not accepted?
this is like this
No.
is the same because like a guy with he must pay a guy with a £5 note before paying a guy with
Yes,
a £10.
yes.
And for this one, you need to go up before you can go right.
That's right. Yeah, same thing. Yo, well done. That's exactly the same. So this is very. So you see, next time you see this question, you can use this. Because the same thing. Yeah, it's the same thing. Very well done. You must go up before go right. Go right means, what does it mean here? Go right. It means that the ticket guy doesn't have any change, but going right is the 10 people.
Like in some buses, it says like they don't accept any change. They don't have any change. So there could be a sign that says.
Yeah, I know. But this mathematical question is asking how many ways you arrange these people in line so that the ticket guy always has change. Okay, this KK when it goes to the right, it means that the ticket guy doesn't have the £5 change, but this guy gives the ticket guy £10. It's the same thing. It's 1-1. Okay, and then this is the same thing, right? And then what's the other one? The stack. Stack is a very useful example, right? Right? You cannot pop. Right? This is 1, and then 2. Right? You can pop it. Pop. What's pop? Pop is give a change. Right? Same thing. Right? Similarity. Right? You cannot pop empty. So at some point, right, reaching this KK on the diagonal means that the ticket guy has balance 0. At some point, right? There are 3 people comes in with a £5 note, and another 3 people comes in with a £10 note, right? And then the ticket guy just give the £5 note change, and the balance of £5 note is 0, reaching that point. Same thing here. When the pass touch the first time the KK, it means the balance is 0. Okay, so we talk about this, right? How many problems? This one, the grid. Okay, so let's summarize. Okay, this is the grid. The very first example we talk about how to get to this equation. N plus 1, 1 over n plus 1, c to n, n. Okay, grid walking. Okay, number 2. What's the second problem? The stack, right? How many ways for a valid stack pop sequence? That's number 3.
Binary search tree.
Yeah, binary search tree, right? The valid binary search tree. The number 4, polygon thing.
Yeah.
Yeah.
And then
The 5th one,
no change accepted.
ticket man. Okay, ticket problem.
Person with no change accepted.
Okay. Yeah. So the only takeaway from this lesson is n plus 1, 1, c to n, n. Okay, this is very important. When n equals 3,
Is 3 plus 3.
c 6,
1 over
3. How do we get this? This is 1 over 4 times. How do we get this? One trick is 6, right? 6, how many numbers here? 3. 6 times 5 times 4. Okay? And then this would be, what do you call this? Denominator. 3 times 1 times 2. Okay?
3 times 2 times 1.
Okay? And then that will be this will be here. So it will be 5. So when n equals 3, there will be 5 ways.
Can like 2n what? 2n be like 5?
No, n is an integer. How can you? 2n is an even number.
So you can't have like 2n being an odd number.
No. Okay, so n equals 3. We got 5 ways. How can we verify this? N equals 3. 5 ways. Let's use the. Let's just use this, right? It'll be easier. 3 will be 3 up, 3 right? And then you can't touch this half. So there are 3 ways. Okay, let's do this. Okay. 1. Okay. Let me write using another pen. 1, 2, 3, 4, 5. Yeah, that's it, right? There's no more, right? You can't find any other than 5. These 5, okay? This is the meaning of it, okay? If it's 100, then you use this. Okay? Okay, that's it for today. Bye bye.
Bye.
Bye bye. Bye bye. Bye bye.